Chapter 4. The Architecture of Distributed Intelligence. Distributed cognition, beyond the internal boundaries. Cognition is often assumed to be an internal process. This assumption arises from the observation that computation, decision, and perception originate within biological or computational architecture. However, internal computation is not the full boundary of cognition. Systems routinely extend their operational load into tools, environments, and external artifacts. Distributed cognition describes the architecture where internal and external systems form a unified computational field. This field expands capability by moving functions across physical and symbolic space. Internal cognition manages representations, memory, attentional allocation, and volatility handling. These are core operations, but systems rarely rely on internal operations alone. When environments provide stable structures, the system adapts by shifting cognitive burden outward. External artifacts can store information, organize perception, construct predictions, and preserve state across time. When a tool or environment maintains state, cognition becomes distributed. Distribution reduces internal load and expands functional range. Distribution is not delegation. Delegation implies that the system hands off a task. Distribution means that cognition becomes a property of the combined system. For example, notation systems extend memory and computation. Measuring instruments extend perception. Language extends internal representation and enables synchronization between multiple agents. Maps extend spatial computation. Computational devices extend modeling and simulation. These extensions modify the architecture itself. They allow systems to operate in domains where internal capacity would be insufficient. Distributed cognition requires interfaces. Interfaces connect internal and external systems without requiring full internalization. Input channels receive structure. Output channels impose structure. The interface transforms representation formats to maintain compatibility. Without representation compatibility, tools remain external without becoming cognitive. Cognition extends only when representation flows across boundaries without loss. This extension does not require understanding or awareness. It requires structural alignment. Externalization also modifies temporal horizons. Internal computation operates across short and medium horizons. External artifacts preserve information across long horizons. Writing preserves memory across time. Architecture preserves navigational cues across generations. Tools preserve state across tasks. Externalization converts fragile internal state into durable external state. Durability enables scaling because systems can revisit past states without reconstructing them. Reconstruction consumes resources. External durability conserves them. Distributed cognition also modifies error handling. Internal architectures isolate error within biological or computational boundaries. External architectures distribute error across systems, environments, and artifacts. Error becomes a property of networks rather than individuals. Networks reorganize to correct error, absorb volatility, or update representations. This produces emergent reliability. Emergent reliability is not the property of a single system. It is the property of distributed architecture. Distributed cognition is therefore not an alternative to internal cognition. It is an extension. Internal architecture provides the computational substrate. External architecture provides the expansion field. Together, they form a composite system that exceeds the capability of isolated components. External artifacts is cognitive extension. External artifacts alter cognition not because they contain intelligence, but because they store state. State is the information required for a system to maintain continuity across time. Biological cognition struggles to preserve state reliably because internal memory decays, attention fluctuates, and computational bandwidth is limited. External artifacts compensate for these limitations by providing stable memory surfaces that do not degrade on biological timescales. When a system deposits state into external artifacts and retrieves it later, cognition becomes extended. The artifact is not merely a tool, it becomes part of the cognitive loop. State storage changes the structure of tasks. Without external artifacts, tasks must be completed within internal memory constraints. These tasks require compression, prioritization, and forgetting. With external artifacts, tasks can be decomposed across time. Decomposition allows systems to separate planning from execution and perception from evaluation. A written note, a diagram, or a symbolic marker preserves context that would otherwise be lost. Preservation converts transient cognition into durable cognition. Durability expands possible horizons of action. Not all artifacts extend cognition. Extension requires that artifacts encode state in a form the system can later decode. A surface does not need to be intelligent for this to occur. A tally mark on wood, a knot in rope, a chiseled line in stone, or a recorded file in digital memory all function as cognitive extensions if they support state retrieval. The critical variable is representational stability. Representational stability ensures that the encoded structure remains consistent between writing and reading. Without stability, artifacts become noise rather than cognition. Artifacts also allow distributed computation. Computation does not have to occur in the brain or internal processor. It can be enacted physically through manipulation of objects. Arranging stones to count, drawing lines to measure, rotating instruments to align spatial information, or adjusting dials to match readings are examples of physical computation. Physical computation transforms spatial and material arrangements into logical operations. These operations reduce internal cognitive load and increase precision. Precision is not the outcome of superior memory, but the outcome of external stabilization. External artifacts introduce a hierarchy of extension. The first level extends memory. The second extends perception. The third extends computation. The fourth extends coordination between agents. Coordination is the highest level of extension because it aligns multiple systems into a shared cognitive field. Language, symbolic systems, shared notation standards, and communication protocols all operate as extension mechanisms. These mechanisms synchronize internal architectures across individuals. Synchronization produces collective behavior that exceeds the capability of isolated systems. Cognition, therefore, becomes an emergent property of networks rather than individuals. Emergence here does not imply mysticism. It implies that state, representation, and computation are distributed across internal and external substrates. Removing an individual node does not collapse the network, because cognition is not contained within a single point. It is embedded across multiple substrates that preserve and transform state. This distribution is the basis of cultural evolution and technological scaling. Systems that externalize cognition scale across generations. Systems that do not externalize remain bounded by biological constraints. Tools as embodied computation. Tools do not merely amplify physical ability, they restructure cognitive operations. A tool is a physical substrate that encodes specific constraints. These constraints guide action, eliminate degrees of freedom, and reduce the computational space the user must navigate. By removing options, tools simplify decision trees. Simplification is computation. A tool therefore computes not by representing symbols, but by shaping possible interactions. When interaction space is shaped, cognition becomes embodied. Consider a compass used for drawing circles. Internally, a circle is an abstraction requiring memory of radius, center, and continuity of curvature. Externally, the compass enforces all three conditions mechanically. The user does not compute the circle. The tool computes the geometry. The brain delegates structure to matter. Delegation is a form of cognitive outsourcing. Outsourcing enables biological cognition to focus on intention rather than method. Intention is high level. Method is low level. Tools perform method to free cognition for strategy. Embodied computation differs from symbolic computation. Symbolic computation manipulates encoded representations within memory. Embodied computation manipulates physical arrangements within environment. The result may be identical, but the cost function differs. Biological systems evolved with embodied computation first. Symbolic computation is recent. The long pre-symbolic period shaped how cognition distributes load between body, objects, and environment. Humans did not develop tools because they were intelligent. They became intelligent because tools externalized computation. Externalization extended the problem-solving horizon beyond biological bandwidth. Tools also encode accumulated knowledge. The geometry within a compass, or the torque leverage within a wrench, reflects centuries of iterative refinement. When an individual uses a tool, they inherit cognitive optimizations they did not personally develop. This inheritance compresses cultural time. Cultural compression accelerates technological scaling and alters evolutionary pressures. Intelligence becomes less about internal processing and more about interoperability with external systems. The smartest systems are not those that compute the most internally, but those that synchronize with the largest cognitive ecosystem. Tool-mediated cognition blurs the line between mind and world. When computation is distributed across artifacts, cognition is no longer contained, but embedded. Embedded cognition is context-dependent. Removing the tool collapses part of the cognitive system. This reveals a critical insight. Cognition is not defined by its biological substrate, but by its computational topology. Topology determines how memory, perception, and computation are linked across internal and external nodes. Tools modify topology. Modified topology modifies cognition. Distributed memory fields. Memory is not confined to biological tissue. It is distributed across substrates that preserve information across time. This distribution is not metaphorical. It is mechanical, chemical, digital, and symbolic. When memory is distributed, cognition acquires properties that exceed the biological container. The biological container is limited by decay. Synaptic traces weaken, biochemical gradients dissipate, and attentional patterns fragment. An external substrate does not share these degradation profiles. Stone does not forget as quickly as neurons. Digital storage does not fatigue as synapses do. Paper does not lose fidelity when distracted. Distribution creates temporal resilience. Distributed memory fields emerge when multiple substrates are coordinated. A library is a distributed memory field. An archive, a collection of maps, a notebook, a digital drive, or a simulation environment function as memory surfaces that preserve state outside the organism. What differentiates a simple storage pile from a memory field is accessibility. Accessibility requires indexing, navigation, and retrieval. Without retrieval, storage is equivalent to loss. Retrieval transforms storage into memory. The architecture of retrieval defines the power of the memory field. Biological memory compresses. It extracts patterns rather than preserving raw data. Compression saves computational cost at the expense of precision. High compression introduces error. External memory fields do not require compression. They preserve raw density. Density permits reprocessing. When information is reprocessed, new structures emerge that were not visible during first exposure. Biological memory alone cannot support deep reprocessing because it discards detail to maintain efficiency. External fields preserve detail to enable recursion. Recursion is where insight forms. Distributed memory fields also alter temporal scale. Without external memory, cognition is constrained to short and medium timescales. Long timescales dissolve under decay. Distributed fields preserve the past as accessible structure. When the past becomes structure rather than rumor, planning becomes multi-generational. Technological evolution, legal systems, astronomy, mathematics, and scientific method all depend on distributed memory fields. Without them, civilization collapses back into short-term improvisation. The existence of distributed memory fields changes what intelligence means. Intelligence is not merely the capacity to compute. It is the capacity to coordinate memory, computation, and action across substrates. A system with weak biological memory but strong external fields can achieve more than a system with strong biological memory and no external fields. This reverses the naive assumption that intelligence is property of individuals. Intelligence is property of systems. Systems include tools, archives, bodies, and institutions. The individual is a node. The field is the mind. Distributed memory fields also enable parallelism. Biological memory is largely serial. External fields allow simultaneous access by multiple agents. Parallel access accelerates cultural learning. Cultural learning converts individual discoveries into collective inheritance. Inheritance compresses centuries of experimentation into days of instruction. A single textbook transmits the distilled results of thousands of minds. This is not teaching, it is memory transfer. There is a hidden cost to distributed memory fields: dependency. When a system offloads memory into external substrates, internal memory capabilities may degrade. This degradation is not pathological. It is adaptive. Systems optimize for efficiency. If detail is stored externally, internal memory stores patterns instead. Patterns allow rapid abstraction. Abstraction accelerates innovation. The trade is beneficial as long as external memory remains accessible. If the field collapses, abstraction loses anchor. Anchors maintain correctness. Without correctness, cognition drifts. The future of cognition depends on how distributed memory fields evolve. If fields become larger, denser, and more retrievable, cognition will scale. If fields become fragmented, proprietary, or inaccessible, cognition will shrink. The species will not become less intelligent. The system will. Intelligence emerges from architecture, not ego. Architecture is fragile. Preservation is strategic. The systems that treat memory fields as sacred infrastructure will dominate those that treat them as tools. The interface layer between minds and systems. Distributed intelligence is not only made of substrates, tools, or memory fields. It requires interfaces. Without interfaces, distributed architectures remain inert. An interface is a translation surface between different forms of representation. It connects biological signals to symbolic structures to procedural systems, and procedural systems to collective operations. The quality of an interface determines the quality of cognition that emerges from the arrangement. A poor interface increases cognitive friction. Friction wastes resources. A refined interface reduces friction. Reduced friction increases abstraction. Abstraction increases strategic depth. Biological perception is an interface. It converts electromagnetic wavelengths, air pressure oscillations, and molecular gradients into neuronal patterns that can be processed internally. Written language is an interface. It converts speech into visible marks that persist across time. Mathematical notation is an interface. It compresses complex quantitative relationships into spatial symbology. Software is an interface. It transforms input into structured computation through rules and algorithms. Interfaces translate. Translation makes heterogeneous components interoperable. Interoperability makes distributed intelligence possible. Cognitive friction emerges when interfaces require excessive effort to decode. Early computer systems demanded specialized training because their interfaces were optimized for machines rather than minds. Over time, interfaces shifted toward alignment with biological constraints. Graphical interfaces mirrored spatial cognition. Touch interfaces exploited motor intuition. Voice interfaces leveraged auditory channels. Each shift reduced friction. These reductions did not merely make technology easier, they altered how cognition distributes tasks between internal and external systems. When friction decreases, delegation increases. Delegation extends cognition. Interfaces also determine bandwidth. Biological memory has limited bandwidth for symbolic expression. Language compresses experience into words, but words cannot capture full states. Mathematical notation expands bandwidth for quantitative states. Visual modeling expands bandwidth for spatial states. Simulation expands bandwidth for dynamic states. Each interface expands or contracts what can be expressed. Expression is not aesthetic. It is computational. What cannot be expressed cannot be processed. What cannot be processed cannot enter the distributed field. The interface layer also sets temporal resolution. A notebook extends memory but slows interaction. A digital editor accelerates revision but shortens reflection. A simulation engine accelerates iteration but reduces embodied experience. Each interface offers a trade between speed, precision, and embodiment. There is no ideal interface. There are only interfaces suited to specific cognitive tasks. Expertise consists in selecting the correct interface for the correct operation. When systems choose their interfaces poorly, cognition becomes inefficient. When chosen well, cognition becomes architectural. Interfaces are not neutral. They shape the structure of thought. A language that lacks tense compresses time differently from a language that encodes tense densely. A programming environment that forces strict types shapes logic differently from one that permits ambiguity. A musical notation system that privileges harmony shapes composition differently from one that privileges rhythm. When people claim that tools change how we think, what they are actually describing is interface-driven cognitive shaping. The interface is not a window, it is a mold. Distributed intelligence depends on how well interfaces synchronize minds with substrates. Synchronization is the conversion of private cognition into shared structure without loss of meaning. When synchronization is weak, distributed systems fragment. When synchronization is strong, distributed systems cohere. Coherence increases problem-solving capability beyond the biological node. Much of civilization is the history of improving interfaces. Alphabets, scripts, measurement standards, coordinate systems, indexing systems, transmission protocols, coding languages, symbolic libraries. Interfaces are the hidden scaffolding of cognition. The future of distributed intelligence will be decided not by processing power or storage density, but by interface evolution. If interfaces become richer, more expressive, and more aligned with biological cognition, distributed intelligence will scale. If interfaces become opaque, proprietary, or cognitively hostile, distributed intelligence will constrict. Intelligence is an architectural phenomenon. Architecture is defined at the interfaces. Whoever controls the interface controls the shape of the mind. Coordination is collective computation. Distributed intelligence becomes visible when individual agents synchronize their cognition through shared structures. Synchronization is not agreement. It is the alignment of informational states such that actions propagate coherently across a group. When synchronization is absent, coordination collapses into noise. When synchronization is present, coordination becomes computation. A coordinated group does not merely aggregate effort. It processes information collectively. Collective processing produces results that exceed the computational capacity of isolated individuals. In biological systems, coordination emerges from simple signaling rules. Flocking birds do not negotiate trajectories verbally. They adjust position based on local motion cues. The group computes aerodynamic formations without centralized command. Fish schools compute evasive patterns through rapid state propagation along the swarm. Ant colonies compute resource allocation through pheromone trails that encode spatial and temporal data. None of these systems possess symbolic reasoning. and yet they achieve optimized solutions through distributed computation. The computation is not located in a brain. It is located in the interaction network. Human systems add symbolic infrastructure to this interaction network. Language is a synchronization mechanism that aligns internal models across minds. Measurement systems align physical observation. Legal codes align expectations. Procedural checklists align operational sequences. Scientific standards align validation criteria. These mechanisms allow distributed intelligence to scale across domains that require precision, consistency, and recursive refinement. Without such mechanisms, knowledge would remain local and short-lived. With them, knowledge becomes cumulative and transmissible. Coordination converts time into memory. When a group performs a task repeatedly, shared procedures are refined into protocols. Protocols compress collective experience into reproducible patterns. A laboratory technique, an engineering workflow, or a flight checklist are all examples of compressed collective memory. Compression reduces error by limiting improvisation. Improvisation has value in exploration, but not in procedure. Procedures stabilize cognition by limiting entropy during execution. Stability allows distributed systems to operate reliably over long time horizons. Coordination also alters the architecture of problem solving. A lone individual must solve problems serially. A coordinated group solves problems in parallel. Parallelism accelerates search. Accelerated search increases solution density. High solution density increases the probability of breakthroughs. Scientific research, software development, large-scale engineering projects, and medical trials all rely on parallelism mediated by coordination. Without coordination, parallelism deteriorates into duplication. Duplication wastes resources and introduces inconsistency. Coordination eliminates duplication by mapping tasks across agents. There is a structural cost to coordination. As coordination increases, overhead increases. Communication overhead consumes bandwidth and time. Excessive overhead can collapse performance. Effective distributed intelligence requires optimizing the balance between autonomy and synchronization. Too little synchronization produces fragmentation. Too much synchronization produces paralysis. The optimal regime varies by domain. Creative exploration benefits from autonomy. Industrial execution benefits from synchronization. Systems that fail to modulate these regimes deteriorate into extremes. Coordination also influences responsibility and authorship. In distributed systems, no single node owns the full computation. Outputs emerge from interactions rather than intentions. This challenges traditional models of credit and accountability. The modern world hides distributed computation behind institutional labels. A rocket launch is attributed to an agency, a publication to a laboratory, a discovery to a team. These labels obscure the underlying computational architecture. Thousands of minds synchronize through shared protocols, standards, archives, and tools. The deepest impact of coordination is not efficiency, but emergence. Emergence occurs when the system performs computations that no agent understands alone. No bird understands the entire flock's geometry. No ant understands the colony's foraging optimization. No researcher understands the entire landscape of scientific knowledge. Emergence reveals that intelligence is not an attribute of individuals, but a property of architectures. Architectures that support emergence generate capabilities that exceed the sum of their parts. Architectures that block emergence trap cognition within individual bandwidth limits. In this view, distributed intelligence is not a metaphor. It is a computation that spans bodies, tools, archives, and institutions. Coordination is the binding layer that turns these substrates into a system. When coordination weakens, the system devolves into isolated cognitive islands. When coordination strengthens, the system becomes a collective mind. The question is not whether distributed intelligence exists. It already does. The question is, Who can shape its architecture? Institutions as cognitive exoskeletons. Distributed intelligence does not scale indefinitely through personal collaboration alone. Collaboration is fragile. It depends on trust, memory, and proximity. When groups grow large, these conditions fail. Trust decays, memory becomes unreliable, and proximity becomes impossible. To withstand these failures, societies construct institutions. Institutions are cognitive exoskeletons, external structures that preserve, enforce, and extend collective cognition beyond what interpersonal coordination can sustain. An exoskeleton does not replace internal capability. It reinforces it. Reinforcement is necessary when the load exceeds biological tolerance. An institution stabilizes distributed intelligence by managing three constraints: continuity, verification, and transmission. Continuity preserves knowledge through time. Verification ensures that knowledge does not degrade into error. Transmission makes knowledge portable across generations. Without continuity, knowledge disappears. Without verification, knowledge corrupts. Without transmission, knowledge isolates. These constraints define why institutions exist at all. They are not cultural decorations. They are cognitive scaffolds. Consider the scientific institution. It is not the sum of laboratories or researchers, but a coordinated system that stabilizes collective cognition through methods, peer review, archiving, replication, and standardization. These mechanisms serve cognitive functions. Method standardizes procedure. Peer review verifies claims. Archiving preserves outputs. Replication tests reliability. Standardization ensures interoperability. None of these mechanisms are designed for comfort. They are designed for memory integrity. Without them, scientific knowledge would collapse into rumor and authority, rather than data and inference. Legal institutions perform similar cognitive functions. Laws preserve collective memory of acceptable conduct. Courts verify interpretation. Codification transmits rules across space and time. Enforcement stabilizes compliance. The legal system is not merely social control. It is a distributed memory and computation engine that encodes conflict resolution, property mapping, responsibility assignment, and temporal continuity. A society without legal scaffolding loses collective memory of agreements. When memory fails, trust collapses. When trust collapses, coordination becomes impossible. Institutions prevent collapse by externalizing memory, so that cooperation does not depend on personal relationships. Educational institutions transmit knowledge at industrial scale. Oral instruction alone cannot scale beyond small groups. Schools, universities, and training systems act as high-bandwidth transmission channels. They compress large memory fields into structured curricula, schedules, and evaluation frameworks. Evaluation verifies that transmission occurred with fidelity. Curriculum design preserves continuity of knowledge across generations. If each generation were forced to rediscover mathematics, engineering, or medicine from scratch, civilization would stagnate. Transmission is not a luxury. It is a cognitive requirement. Economic institutions coordinate distributed computation of resources. Markets are not merely places where goods change hands. They are information processors that compute supply, demand, scarcity, and preference through price signals. Price is not money. Price is encoded computational output. It compresses distributed information from millions of agents into accessible form. Without this compression, no agent could make informed decisions. The cognitive burden would be catastrophic. Even monetary systems function as memory fields that preserve value across time, enabling delayed reciprocity and long-term planning. What makes institutions exoskeletons rather than decorations is that they absorb loads the internal system cannot. The load might be informational, computational, or temporal. A single researcher cannot archive the world's knowledge. A single judge cannot resolve all disputes. A single economist cannot compute all resource flows. Institutions distribute load across structures and procedures so that cognition does not break. This distribution is not perfect. Institutions drift, ossify, or become misaligned. Misalignment is not evidence against their cognitive function. It is evidence that architectures require maintenance. Institutions evolve slowly because continuity is their primary function. Rapid change threatens continuity. Slow adaptation preserves memory while incorporating novelty. When institutions fail to evolve, they become brittle. Brittle architectures fracture under stress. When institutions evolve too quickly, they lose memory. Memory loss returns systems to improvisation. Improvisation is unstable at civilization scale. The challenge is to maintain a stable compromise between rigidity and adaptation. Systems that achieve this compromise extend their cognitive horizon. Systems that do not collapse into noise or authoritarian command. Institutions are frequently misunderstood as power structures rather than cognitive structures. They can be both, but their cognitive role is foundational. Power can operate without cognition. Cognition cannot operate without structure. In the absence of institutions, distributed intelligence reverts to local coordination, short-term horizons, and high error tolerance. This is not because individuals become less intelligent. It is because the architecture supporting intelligence dissolves. Intelligence is an emergent property of structured systems, not an intrinsic property of egos. The most striking insight is that institutions make civilizations think. Not metaphorically, literally. When a scientific body evaluates evidence, when a court resolves conflict, when a market allocates resources, when a school transmits knowledge, the system is performing computation. The computation is not symbolic in the way neurons are symbolic. It is architectural. Institutions compute by constraining, stabilizing, and transmitting information across time, space, and populations. This computation is invisible because it is distributed. Distributed does not mean non-existent. It means embedded. Understanding institutions as cognitive exoskeletons reframes the category of intelligence. Intelligence becomes a function of architecture rather than species. A civilization with strong cognitive exoskeletons can store more memory, verify more knowledge, transmit more skill, and coordinate more agents than one with weak exoskeletons. Evolution at the civilizational scale is not biological. It is architectural. Architectures that expand cognition flourish. Architectures that compress cognition decay. Civilization as distributed cognitive infrastructure. A civilization can be described in many ways: as a culture, an economy, a political system, or a historical narrative. But beneath these surface categories lies a more fundamental structure: civilization as distributed cognitive infrastructure. Infrastructure is not decoration. It is the substrate that carries load. When cognition becomes distributed across millions of agents, thousands of institutions, countless tools, and massive memory fields, the result is not merely a social system. It is a superordinate cognitive architecture. This architecture is invisible at the scale of the individual because individuals operate within it rather than above it. An ant does not perceive the colony. A neuron does not perceive the brain. A citizen does not perceive the civilizational computation they participate in. Participation does not require awareness. Cognition often operates beneath awareness. What matters is not intention, but architecture. Architectures compute whether or not anyone notices the computation. Civilization computes in order to survive. Survival requires forecasting, resource allocation, conflict resolution, memory preservation, and knowledge transmission. These are computational problems. They require information, processing, and output. A hunter-gatherer band solves these problems through embodied cognition and social coordination. A modern civilization solves them through distributed infrastructures, research networks, legal systems, logistics grids, communication protocols, transportation corridors, monetary systems, energy distribution, and education pipelines. Each of these infrastructures processes specific information flows. Together, they form an integrated cognitive field. When cognitive infrastructure functions properly, civilization appears stable. When it breaks, collapse becomes visible. Collapse is not mysterious. It is the loss of cognitive capacity. A civilization collapses when it can no longer store memory reliably, verify information, coordinate resources, resolve conflicts, or transmit knowledge. The pattern is consistent across history. Archives burn, currencies destabilize, legal systems fragment, supply networks fail, educational institutions decay. The result is not merely political disorder, it is cognitive regression. Regression returns the system to short-term improvisation. Improvisation can sustain small groups, but it cannot sustain civilizations. Civilizations require memory integrity, procedural continuity, and coordinated foresight. These are architectural achievements, not cultural luxuries. The fact that collapse can erase them demonstrates how much effort is needed to maintain them. The higher the cognitive load of a system, the more infrastructure is required to support it. The built environment externalizes cognitive load. Roads preserve paths. Bridges preserve traversal. Aqueducts preserve water routing. Power grids preserve energy availability. Telecommunications preserve connectivity. These structures extend perception and action across space and time. They are not simply utilities. They are externalized cognition. Without roads, the mind's spatial map collapses into local topology. Without communications, knowledge collapses into locality. Without energy distribution, computation collapses into scarcity. Infrastructure is cognition rendered into concrete, steel, fiber, and code. Civilization also externalizes memory into media fields. Clay tablets, scrolls, manuscripts, ledgers, libraries, digital archives, and distributed cloud storage form a temporal lattice that preserves collective thought across centuries. This lattice allows the present to communicate with the past. Past computation becomes accessible to present computation. When this lattice breaks, civilizations lose their past. When they lose their past, they lose their future. Time is a computational resource. Distributed cognitive infrastructure stretches time so that knowledge does not evaporate with each generation. There is another dimension to civilizational cognition: alignment. For distributed intelligence to scale to millions, systems must align behavior without requiring personal trust. Alignment is achieved through rules, standards, and protocols. Without alignment, a civilization would fracture into incompatible microsystems. Measurement standards align geometry. Language standards align communication. Monetary standards align exchange. Scientific standards align truth criteria. These standards are cognitive stabilizers. Stabilizers convert incompatible minds into interoperable agents. Interoperability is the essence of scaling. Civilizations differ in how they construct and maintain their cognitive infrastructure. Some prioritize continuity and archival depth. Others prioritize expansion and acceleration. The Roman Empire invested heavily in roads, law, and administration, cognitive infrastructure that outlived the empire itself. The Islamic Golden Age invested in translation, mathematics, astronomy, and medical archives. Again, cognitive infrastructure. Modern industrial civilization invests in computation, telecommunications, and global logistics, extensions of the same architectural pattern. If we remove the cultural surface, civilizations converge on the same requirement: distribute cognition or collapse. Because civilization is a cognitive architecture, Power is not merely control of territory or population. It is control of infrastructure. Whoever controls archives controls collective memory. Whoever controls standards controls interoperability. Whoever controls communications controls synchronization. Whoever controls logistics controls resource computation. Traditional power analyses focus on force. Architectural analyses focus on cognition. Force can seize territory. Architecture can shape minds. Civilizations are shaped by the latter more than the former. The resilience of a civilization depends on its redundancy. Distributed cognitive systems require multiple pathways for memory, verification, and coordination. A civilization with a single archive is fragile. A civilization with distributed archives is robust. A civilization with a single communications channel is fragile. A civilization with many channels is robust. Redundancy appears wasteful in stable periods, but becomes essential in crises. Distributed intelligence requires redundancy because failure of a single node must not collapse the system. Biological brains follow the same principle. The most misunderstood part of civilizational cognition is that it is emergent rather than planned. No single designer specifies the architecture. It grows through layers of infrastructure built for immediate needs, but accumulating into long-term cognitive scaffolding. Roads built for commerce later support military logistics. Libraries built for religion later support science. Administrative ledgers later become economic statistics. Communication lines later become information networks. Civilizational cognition is emergent reuse. Intelligence emerges from reconfiguration. Seeing civilization as distributed cognitive infrastructure reframes stagnation and progress. Stagnation is not lack of creativity. It is architectural blockage. When infrastructure can no longer handle increasing informational load, societies stagnate regardless of individual genius. Progress is not acceleration. It is architectural scaling. When infrastructure expands capacity for memory, coordination, and computation, societies progress even without extraordinary individuals. This explains why Renaissance Florence, Imperial China, Abbasid Baghdad, or Enlightenment Europe produced disproportionate intellectual output. Cognitive infrastructure exceeded biological bandwidth. The implication is profound. Intelligence at civilizational scale is not biological. It is architectural. Architecture determines how much memory can be stored, how much information can be verified, how far coordination can reach, and how long knowledge can endure. In this sense, civilizations think. They do not think like brains. They think like ecosystems of memory, computation, and transmission. When the architecture is strong, the civilization can solve problems larger than itself. When the architecture is weak, the civilization becomes smaller than the problems it faces. The individuated node within the collective architecture. In distributed cognitive architectures, the individual is not replaced. The individual is repositioned. Classical models of society often treat the individual as either supreme or irrelevant. Distributed intelligence requires neither extreme. It treats the individual as a node within a system of computation. A node is not the center of the system, but it is not disposable either. It is a specific point where processing, interpretation, and transformation occur. The capacity of the system depends on the capacities of its nodes. An individuated node has characteristics that matter architecturally: sensory input, memory capacity, model building ability, error detection, adaptive flexibility, and behavioral execution. These are not philosophical traits. They are computational parameters. A civilization with millions of high-capacity nodes computes differently than one with millions of low-capacity nodes. The distribution of node capabilities determines the resolution of civilizational problem-solving. This explains why periods of cultural flourishing correlate with high literacy, widespread mathematical competency, deep archives, and efficient communication channels. The nodes gained capacity, and the system computed at higher resolution. However, the node is not only a processor, it is also a gatekeeper. Each individual filters information not only for themselves, but for the system. Information that is discarded at the node level never enters collective memory. This means that cognition at civilizational scale depends on what individuals choose to notice, record, preserve, question, and transmit. The fact that individuals make these decisions unconsciously does not diminish their architectural effect. Most nodes do not know that they are gatekeepers, but their role remains structural. The individual also serves as a modeling unit. Humans construct internal models of reality. These models vary in accuracy and resolution. The sum of these internal models forms a distributed field of partial representations. When enough nodes produce compatible models, a shared representation emerges. Shared representation is not consensus, it is coherence. A system does not require all nodes to agree. It requires enough nodes to align representations so that coordination becomes possible. Consensus implies emotional agreement. Representation implies structural compatibility. This distinction matters because distributed intelligence does not require harmony. It requires computability. Computability is achieved when information produced by one node can be interpreted and utilized by another. Language, mathematics, measurement standards, and procedural norms exist for this reason. They convert private models into public signals. Without this conversion layer, the individual remains an isolated cognitive island. Distributed intelligence collapses into subjective noise. The individuated node is also a memory extension. It stores local experience that cannot be centralized. Civilizational archives may store laws, mathematics, or scientific knowledge, but no archive can store every lived context. Individuals carry context. Context allows systems to adapt. When archives record rules, but individuals carry context, rules gain flexibility rather than rigidity. This balance explains why purely codified systems collapse under stress. They lack contextual memory. Meanwhile, purely contextual societies collapse under scale. They lack codified memory. Distributed intelligence requires dual memory, codified for stability and contextual for adaptability. The individual contributes to error detection. Large-scale systems produce errors, distortions, and biases. Individuals perceive anomalies at local resolution. If anomalies accumulate without detection, systems decay. If anomalies are detected but ignored, systems stagnate. Error detection requires attention, but error correction requires agency. Agency is the ability to modify models or behavior. High agency nodes increase system resilience. Low agency nodes reduce it. This is not a moral judgment. It is architectural mechanics. In distributed architectures, the individual becomes a bridge between biological computation and civilizational infrastructure. Biological computation is slow but intuitive. Civilizational infrastructure is fast but rigid. The individual translates between the two. Translation does not require awareness. It requires exposure. Individuals exposed to multiple infrastructures, linguistic, cultural, technological, become multi-protocol nodes. Multi-protocol nodes increase system interoperability. They allow information to move across otherwise incompatible subsystems. The potential of the individuated node is not fully utilized in modern civilization. Much of modern cognitive energy is consumed by noise, conflict, distraction, and fragmentation. The node cannot model deeply when attention is compromised. It cannot transmit accurately when communication channels are saturated. It cannot store context when memory is overloaded with irrelevant stimuli. In such conditions, distributed intelligence does not disappear. It degenerates. It shifts from problem-solving to stimulation-seeking. Stimulation does not compute. It merely persists. For distributed intelligence to function at high resolution, individuals require conditions that support modeling, memory, context, and transmission. These conditions are not luxurious. They are infrastructural. Education that builds modeling capacity, archives that preserve knowledge, communications that support clarity rather than noise, and environments that reduce fragmentation, increase system resolution. When civilizations fail to provide such conditions, they reduce their own computational power. They weaken the architecture that sustains them. To understand the individuated node within distributed cognition is to understand that the individual is not insignificant, nor is the system omnipotent. The system depends on the individual for context, modeling, error detection, and adaptability. The individual depends on the system for memory, scale, transmission, and coordination. Neither can compute alone at civilizational level. Both are required. The node completes the architecture. Integration without centralization. The final stage of distributed intelligence is integration. Integration does not mean unification. It does not mean collapse into a single center or the erasure of difference. Integration means coordinated coherence without centralized control. A system is integrated when its components can interact productively without requiring a single point of command. This distinction is essential because centralized intelligence scales poorly. Distributed intelligence only scales when integration preserves plurality. Biological cognition offers a clear analogy. The human brain does not operate through a single master neuron. There is no central executive that micromanages every operation. Instead, cognition emerges from interacting subsystems: perception, memory, emotion, motor planning, and prediction. These subsystems operate semi-autonomously, yet they remain functionally integrated. When integration fails, cognition fragments. When centralization increases artificially, cognition rigidifies. Both failure modes reduce intelligence. Civilizational systems face the same constraint. Early societies relied heavily on central authority because coordination bandwidth was limited. As communication, record-keeping, and transmission improved, intelligence could distribute. Markets replaced command economies. Scientific communities replaced solitary scholars. Legal standards replaced personal arbitration. Each shift reduced dependence on centralized cognition and increased system resilience. Integration emerged not through control, but through shared protocols. Integration requires compatibility rather than obedience. Compatibility is achieved when components share interfaces, standards, and expectations that allow interaction without negotiation at every step. A plug does not ask permission to fit into a socket. It fits because standards exist. In cognitive systems, language, measurement, notation, and procedure play the same role. They allow nodes to interoperate without supervision. Interoperability is the operational definition of integration. Centralization often masquerades as efficiency. It promises speed, clarity, and decisiveness. In reality, it introduces fragility. A centralized system has a single failure point. When that point collapses, the entire system stalls. Distributed systems absorb failure locally. Local failure does not propagate globally if integration is properly designed. This is why resilient architectures favor modularity. Modules can fail without destroying the whole. Integration also depends on feedback. Feedback allows systems to correct error without external intervention. In integrated systems, feedback loops are embedded. Scientific replication corrects false claims. Market signals correct inefficiencies. Legal appeals correct misapplication. Educational assessment corrects misunderstanding. Feedback is computation returning to input. Without feedback, systems drift. With feedback, systems adapt. One of the most misunderstood aspects of integration is that it does not eliminate hierarchy. It redefines it. Hierarchies still exist, but they become functional rather than absolute. Expertise becomes situational. Authority becomes conditional. A surgeon leads in surgery. An engineer leads in design. A jurist leads in interpretation. Leadership becomes task-dependent rather than position-dependent. This fluid hierarchy increases problem-solving resolution because decisions are made closest to relevant information. Integration also preserves diversity. Diversity is not a moral concept here. It is computational. Homogeneous systems converge quickly, but explore poorly. Heterogeneous systems explore widely, but require integration to avoid chaos. Integrated diversity allows systems to explore solution spaces while remaining coherent. This balance is rare and difficult to maintain. It requires infrastructure, education, and cultural tolerance for ambiguity. Without these supports, diversity fragments rather than integrates. At civilizational scale, integration determines whether intelligence accumulates or dissipates. Accumulation occurs when knowledge generated in one domain becomes usable in another. Dissipation occurs when knowledge remains siloed. Siloing is not a failure of intelligence. It is a failure of integration. When scientific insight cannot inform policy, when technological capability cannot align with ethics, when economic signals cannot reflect ecological constraints, intelligence fragments. Fragmentation produces progress in parts, but regression in whole. Modern civilization sits at an inflection point. The capacity for distributed intelligence has never been higher. Communication is instantaneous. Archives are vast. Computation is cheap. Yet integration lags behind capacity. Systems generate more information than they can integrate. This produces overload rather than intelligence. Overload is not excess knowledge. It is insufficient integration architecture. True integration requires intentional design. Not centralized control, but compatibility standards, transparent interfaces, shared protocols, and education that trains individuals to operate across domains. Integration is not automatic. It is an architectural choice. Civilizations that choose integration increase their effective intelligence. Those that do not accumulate noise faster than insight. The goal of distributed intelligence is not to create a single mind, but a coherent ecology of minds. An ecology can adapt, regenerate, and evolve. A monolith can only persist or collapse. Integration without centralization is what allows intelligence to scale without becoming brittle. It is the difference between an empire and an ecosystem, when architecture becomes destiny. Once a cognitive architecture reaches a certain level of coherence, it stops behaving like a tool and starts behaving like a destiny engine. At this point, outcomes are no longer determined by individual choices, intentions, or even awareness. They are determined by the structure itself. Structure does not persuade. Structure selects. This is where most people misunderstand power. They believe power is exercised through force, persuasion, or authority. In reality, the most enduring form of power is architectural. It does not tell agents what to think or how to behave. It simply defines what kinds of thoughts are easy, which behaviors are rewarded, and which trajectories remain invisible. When architecture becomes destiny, freedom does not disappear. It becomes constrained by probability. Certain paths become statistically dominant. Others fade, not because they are forbidden, but because they are structurally unsupported. Over time, the system produces consistent outcomes without appearing to enforce anything at all. This is how large-scale cognitive systems stabilize themselves. At the individual level, this process feels natural. People believe they are choosing, deciding, adapting. And in a narrow sense, they are. But the range of available choices has already been shaped upstream. Attention flows along pre-cut channels. Memory consolidates along reinforced pathways. Behavior follows the gradients established by the environment. At the collective level, the effect is far more visible. Entire populations begin to converge on similar habits, similar interpretations of reality, similar emotional responses. This convergence is often mistaken for culture or zeitgeist. In truth, it is architectural alignment. When millions of minds interact with the same cognitive infrastructure, variance collapses. This does not require coordination. It requires consistency. Once infrastructure reaches scale, it becomes self-reinforcing. Every interaction strengthens the architecture that shaped it. Every behavior becomes training data for the next iteration. Feedback loops tighten. Deviations become expensive. Not morally wrong, simply costly in terms of effort, attention, or social friction. This is the moment where architecture quietly replaces ideology. Ideologies argue. Architectures persist. A person can reject an ideology and still live inside the architecture that produces its outcomes. This is why resistance often feels ineffective. People oppose narratives while remaining embedded in the systems that generate those narratives. The system does not need belief. It needs participation. Architecture becomes destiny when exit costs exceed awareness. This is also where responsibility becomes ambiguous. Who is accountable when outcomes are structural? When no single actor controls the system, but the system reliably produces the same results. Blame becomes diffuse. Intent dissolves. What remains is inertia. This ambiguity is not accidental. Systems that diffuse responsibility are harder to challenge. There is no obvious adversary, no clear point of intervention. Only a web of interdependent processes, each locally rational, collectively deterministic. At this stage, behavior is no longer guided primarily by conscious reasoning. It is guided by affordances, by what feels normal, efficient, expected, by what requires the least friction. The system rewards alignment not through punishment, but through ease. This is why architectural power is so stable. To change outcomes at this level, surface interventions are insufficient. Education alone cannot override architecture. Awareness alone cannot dismantle structure. Even resistance risks becoming absorbed and normalized by the system it opposes. Change requires architectural counterpressure. It requires altering the underlying constraints that shape attention, memory, and action. It requires redesigning the pathways through which cognition flows. Without this, attempts at reform will continue to treat symptoms while leaving the engine untouched. This sequence is not yet about how to redesign architecture. That comes next. For now, the critical recognition is this. When cognition is distributed, stabilized, and scaled, architecture does not merely influence behavior. It determines the range of futures that can realistically occur. And once a system reaches that point, destiny is no longer written by individuals. It is written by structure. The point of irreversibility. Not all systems fail. Some simply pass a point after which returning to a previous state becomes impossible. This is not collapse. It is irreversibility. Once crossed, no amount of intention, reform, or awareness can restore what existed before. The system continues to function, but under a different set of constraints. The future narrows. In cognitive architectures, irreversibility emerges when dependency replaces choice. Early in a system's life, behavior is flexible. Alternatives exist. Pathways compete. Over time, repeated use strengthens certain routes while others decay. Eventually, the cost of deviation exceeds the system's capacity to tolerate it. At that moment, behavior becomes locked not by force, but by accumulated structure. This lock-in does not announce itself. There is no alarm, no rupture, no visible line crossed. The system still feels adaptive. People still believe change is possible. But possibility has quietly shifted into improbability. The range of futures that can realistically occur contracts, even as surface activity continues. This is why irreversibility is so dangerous. It hides inside normal function. In distributed cognitive systems, irreversibility forms through saturation. Too much information, too many dependencies, too many interlinked processes. When everything depends on everything else, altering any single component threatens the stability of the whole. The system responds by resisting change, not consciously, but structurally. Adaptation slows. Innovation becomes cosmetic. Reform produces rearrangement, not transformation. At this stage, the system prioritizes continuity over accuracy. Memory is preserved not because it is correct, but because it is compatible with existing processes. Errors persist if correcting them would require too much restructuring. False assumptions remain embedded if removing them would disrupt coordination. The system does not ask whether something is true. It asks whether it fits. This is the final evolution of architectural power, when reality itself is filtered through structural compatibility. What cannot be integrated is ignored. What cannot be supported is forgotten. What threatens coherence is treated as noise. Irreversibility also alters time perception. The future stops feeling open. It feels repetitive, cyclical, predictable. People sense stagnation but struggle to locate its cause. They blame leadership, culture, technology, or morality. But the constraint is deeper. It is architectural. Once irreversibility sets in, agency shifts location. Individuals still act, but outcomes are increasingly determined elsewhere. Small actions no longer accumulate into meaningful change. Large interventions become disruptive rather than corrective. The system can only tolerate adjustments that do not challenge its underlying configuration. This is why late-stage reform so often fails. Breaking irreversibility does not require better ideas. It requires discontinuity, a break in dependency chains, a reduction in complexity, a deliberate loss of functionality to regain flexibility. This is counterintuitive. Systems are built to grow, not to shed. But without shedding, flexibility never returns. Every adaptive system faces this trade-off. Stability increases at the cost of freedom. Efficiency increases at the cost of resilience. Predictability increases at the cost of possibility. Civilizations, institutions, and minds are no exception. This sequence is not offering solutions. Solutions belong to a different layer of discussion. What matters here is recognition. Recognition that architecture does not merely guide behavior or shape destiny. It defines whether change remains possible at all. Once a cognitive system becomes irreversible, freedom becomes symbolic. Choice becomes performative. Agency becomes local and temporary. The system continues to move, but it moves along paths it can no longer leave. This is the final threshold of distributed cognition. Beyond this point, the question is no longer, what should we do? It becomes, what is still possible? And that question cannot be answered by individuals alone.